Mid-ocean ridge paleomagnetism. Introduction. As molten lava cools, its iron minerals line up in the direction of the Earth's magnetic field. As early as 1906, it was noticed that some rocks were magnetized in the opposite direction, as if the Earth's north and south poles had switched places. It is now known that the poles may have flipped many times during the geologic past, creating periods of normal magnetism, as today, and periods where the magnetic fields were reversed. In 1963, it was proposed that the new oceanic crust is created at the mid-ocean ridges by lava welling up from the interior in a process called sea floor spreading. If so, rocks of the mid-ocean ridge should preserve a record of the periods of normal and reverse magnetism. If we measure the strength of the Earth's magnetic field across the ridge, a series of anomalies or differences should occur. Where rocks that solidified during normal magnetism are found, these should have high values of magnetism. These should have high values because the magnetism introduced in them adds to the current field strength. Where rocks solidified during reverse magnetism, low value should be found because the reversed rocks reduce the local effect of the Earth's present magnetic field. When magnetic anomalies are mapped, alternating bands of high and low magnetism should appear that are symmetrical with the axis of the ridge. Such a pattern provides strong evidence that seafloor spreading is the process that forms the ocean basin and moves continents. All right.
That was a tough one.
All right, so in this diagram, we can see that there is rising magma on either side going into a volcano. These volcanoes over here. And then we see this is the sea floor spreading. You can see the rising magma into the mid-ocean ridge. Then the mantle, the subduction zone where the lava goes underneath the land masses. And we can also see alternating bands of polarity and magnetism here denoted by the shading and the direction. If you notice, the arrows are pointing out, so the seafloor is spreading. And the scale is in millions of years ago. The blocks are in millions of years. All right, so. Procedure. On diagram A, the geometric time scale, color all the time periods that have normal magnetism in the magnetism column. Number 2, draw a line across the age scale that represents now, 1 million years ago, 2 million years ago, 3 million years ago, and 4 million years ago onto the magnetism column. Label each line with a different color to represent each time period and complete the key on diagram B. Number 3, cut off the age column of diagram A. Number 4, cut out the magnetism column and cut it in half lengthwise, forming 2 strips. Number 5, staple/tape the strips together on the line labeled now. Number 6, on diagram B, label the lines for the mid-ocean ridge, slit B, the rift. At the subduction zones, slits A and C, label lines trench. See diagram C below. Number 7, cut along the bold lines for slits A and B and C. Number 8, insert the slip showing magnetism into the mid-ocean ridge slip B, as seen in the diagram below. This shows new material forming at the rift. Tape the tab on the now to the back of diagram B. Number 9. Thread one end of the slip through slit A and the other end of the slip through slip C, as seen in the diagram to show subduction at the trenches. Number 10. Slowly pull the two ends of the strip so you can see 4 million years ago, 3 million years ago, 2 million years ago, and now. And this is the diagram showing you how to put in the slips. That way you can see the subduction zones in the new magma. This is diagram C. That should be. Oh, wait, no, there's questions. All right, it's still recording. Now to the questions. Questions, class textbook, page 174 to 177. Number 1, what is happening at slit B? Number 2, what feature occurs at the corresponding location, slit B, on the seafloor? A, deep ocean trench. B, mid-ocean ridge. C, hotspot. Number 3, what is happening at slits A and C? Number 4, what feature occurs at the corresponding location on the seafloor? A, deep ocean trench. B, mid-ocean ridge. C, hotspot. Number 5, if you were to sample and date the rocks, which band of rock is the youngest? The rock closest to the ridge, slit B. The rock that is furthest from the ridge, slit A. Number 6, how do you know this band of rock is the youngest? A, the lava is cooling and formed a new rock along the ridge. B, the lava is cooling only at slit A. C, the lava is cooling at the furthest point from the ridge. Number 7, where are the oldest bands of rock? Choice A, the rock closest to the ridge. Choice B, the rock furthest from the ridge. Number 8, heat flow is a measure of the amount of heat leaving the rocks of the lithosphere. As distance from the spreading center, mid-ocean ridge, increases, what happens to the heat flow? The heat flow will A, increases, B, decreases, C, remains the same. Question 9. Where would heat flow be the greatest? Near the ridge where the lava is cooling. B, at the subduction zone where the plate goes backwards towards the mantle. C, the heat flow is the same all over the ocean floor. Number 10, do magnetic reversals occur at regular intervals through time? Yes or no? And that is the end of the